Hi, thanks for coming to my poster. So this project brings together work in two areas. The first is drug safety, which simply asks if taking a particular drug, here labeled drug A, has a measurable effect on whether you develop some particular outcome Y. And the second area is dimensionality reduction in health data. So the health data we're working with looks something like this: a timeline of one person's health history, all the diagnoses and medical interventions they have. And these are coded data, so we're dealing with many possible codes, creating high dimensionality. Previous work has worked on reducing the dimensionality, but here we're going to ask, how can we reduce dimensionality in a way that's useful for drug safety studies? So these drug safety studies are typically done using cohort study design. In this approach, an expert crafts a comparator cohort for the treated cohort of people who should be in similar health. So we start from our electronic health record population, and if our drug A is an anti-epileptic, an expert will craft a comparative cohort taking drug C, maybe another anti-epileptic. But still, people taking drug A might be younger or might have a history of other drugs. And if their medical history or age changes their risk of developing the outcome Y, such as younger people are at less risk of developing the outcome Y, this can create confounding. So we deal with this by matching on key confounders, and we keep only the matched sets of people. Then in our matched sets, people on drug A will be no older than people on drug C, and there will be no more confounding effect. So finally, when we have our two matched sets of people, we can look at what happens after they take their drugs and see if either group is more or less likely to get the outcome Y. So this is a great method, but it relies on expert design. Experts need to pick that comparator drug, the comparable anti-epileptic, and they also need to figure out what are the key confounders we need to control for. So how would it look if we tried to do matching without the expert? How can we tell if these two people, one taking drug A and the other taking drug C, are a good match without an expert telling us the few key things to match on? So people's histories in the time before they took drug A could be encoded into this big high-dimensional vector. And this vector is a simplification of health history, but it's already a huge vector. And we can create these vectors for each of this pair of people, but how do you compare these two people to each other? We can just say that they don't have identical health histories because we've lost all meaning by encoding the medical history this way. If we had the meaning, if we knew that the person on drug A had a history of anticoagulants and dysrhythmia, and the person on drug C has atrial fibrillation, we would know they actually do have very similar health history. So what we want to do is map down these huge high-dimensional vectors into something lower dimensional that's useful for matching because it retains the meaning of the medical codes. So we're going to learn these vectors that retain the meaning, embedding vectors, by training on the health data using a neural network. So how this works is I chop up people's health histories into training examples of a pair of something that happened in their health history and the drug that followed it. And we feed these vectors into the neural network, and it looks up the current version of the vectors, and we'll know if that version is good if it's useful for this training task of predicting what drug follows that particular history event. So over the course of many training pairs, our vectors become very good for this training task of predicting what drug comes next. So let's get some intuition for the vectors. The vectors for the drug embeddings are trained so that drugs that are given in the most similar health context will have the closest vectors. So two different drugs that follow a diagnosis for diabetes would have very similar vectors. And the indication embeddings are trained so that they represent the health context that leads to prescribing of a new drug. So two different codes that lead to prescription of the same drug would have very similar vectors. So there are about 30,000 drugs, diseases, and procedures that we create these embedding vectors for, and we can visualize these using UMAP. So here each point is one medical code, and I highlighted some codes corresponding to dysrhythmia and anticoagulants that sometimes treat dysrhythmia. So you can see that there's a lot of meaning captured there. And then I show that these are useful for the task of first using the drug embeddings to find a suitable comparator drug, And second, the other expert task of matching on confounding health status leading to treatment. So this paper is now published in AMIA Open. You can go to my website to find it. Also, the embeddings are freely downloadable that you can use for your own study using standardized codes. Finally, I'm looking for students, and the contact info for that is on my website.